Okay, let's see. Chat. Okay, let's see. Oh, there's Mead. Hey, what's up, Mead?
Hi.
I can't hear you that well. Hold on.
Really? You want me to go get the mic?
Oh, no, I can hear you now. I just turned up the volume a little bit. There are 2 viewers. Oh, wait, there's one. It just keeps flipping on and off.
Whoa.
Okay. What's up?
Nothing. I just saw a live stream of my own face.
Oh, yeah. Actually, let me, so it doesn't keep switching, let me do present screen share and then present to everyone, so that way it won't keep switching whenever we talk.
Perfect.
Yep, that was different. We'll call this Google Hangout. Did you post it in the Facebook? I don't know if
Sure. Yeah, 1 second.
I told them that you would, like, I would post a YouTube link unless they actually want to be on webcam.
So how is this gonna work?
So you can do one of 2 things. Okay, they can either just watch through YouTube while we're live streaming this, or if they want to actually be in the conversation, you'd have to send them that link that I said,
Okay.
the Hangouts.Google one. If they have Google Plus, they can jump that in the call. But if they just want to watch, like, in the background and stuff like that, then I would click on the YouTube link.
All right. I'll post that then.
Okay. And I have group chat enabled, so I guess, but I guess that's only for people that are in the call.
Yeah, I think so.
I don't know what Q&A. Q&A says disabled. I don't understand why. Why is Q&A disabled? Let's see. Q&A app. Oh. Oh, you have to turn on before. Okay, never mind. Q&A doesn't really matter. Okay. How's everything going?
Good. I just posted this, and I'm up to chapter 5 in the review book, which I hope.
Oh, nice. Okay, Abraham's in here, so let me see if copy link address. I don't know if he's watching or if he's going to join. Oh, shoot.
You okay?
Yeah, no, I'm putting. You want? Sorry, I sent an invite to Abraham because he added me on. Show. Oh, he's watching. Okay. So there's Abraham. How's the review book working out for you?
I think a review book's great. I mean, for like 2 nights before exam reviewing, it's really nice. It's concise.
Okay.
You can just
Gotcha. Yeah, it's definitely only useful if you've already learned 90% of the material.
Yep.
Okay, so let's see. Do you have something you want to talk about? I kind of want. Oh, Claire's here. Guess I'll add her on Google.
How do you see this? Oh, I see.
Yeah, she's up next to that. Let's see.
Okay.
Add to circles. IB chemistry. Claire?
Yeah.
Okay. All right. I think. Okay. So did you put both links up, Nick?
Yeah.
Okay. So I think there's a limit to how many people can be in the Google Hangout. So we'll just see, but we'll play it by ear.
Or
Okay. We'll give them a couple more minutes, and then we'll get started. Do you have any particular that you want to start about?
I have some questions.
Yeah. Shoot. Like, are they sporadic? Or are they like a theme?
Wait, are they specific to like a certain thing?
Yeah.
I have two that are kind of related.
Okay. Let me write them down.
Okay. I wanted to know about if like the IB would expect you to know like the spectrochemical series like for paper 1, and if there's like really like a rule for that other than it's in your data booklet.
Oh, wait. So you're talking about the ligands?
Yeah.
No, they don't expect you to memorize that.
Oh, okay.
Okay.
And then I was wondering, maybe this isn't such a great question for like review mode, but I don't really understand like why having an incomplete D sublevel like allows transition metals to bond with like 5 different ligands. I mean, not 5 different ligands, but like 5 ligands.
5 ligands. Well, it's kind of like the expanded octet with. Well, okay. So the D sublevels available for dative covalent bonding. So it's the fact that they just have empty orbitals and it's positively charged that attracts. Because what you want to think about is, like, for example, let's say iron, for example, okay, is 4s this, right? And so when it loses 2 electrons, you have this left, this 3D. And these partially filled sublevels allow for the ligands to attach to them.
Okay.
Because that's the outermost level now.
But isn't that only 4 though?
Well, that actually, well, hold on a second. So the dative covalent bonding occurs, it occurs in the 4th energy level. No, okay, sorry. I'm thinking I'm saying this wrong. So the 4th energy level is where the empty subshell, the ligands bond into, because they're empty orbitals. Okay? These are the ones that affect color.
Okay.
So the fact that the ligands are attaching to that empty 4th energy level then splits the D sublevel. Okay? It splits this into, you don't need to know like the actual separation, like, but essentially it splits here so the electrons are able to jump up and absorb certain frequencies of light.
Right.
So that's the idea there. You don't necessarily need to know like how that works.
Okay.
But that's the general idea there.
Okay. And it's always like, no matter what the metal is, it's always 5 ligands, and it forms that octahedral.
My rule of thumb generally is that the best way to do it is you double the charge.
Okay.
So double charge to determine ligands for transition metals. Aluminum's a little different. It can only have a maximum of 4 because remember, aluminum is not in the transition metals, so it doesn't have the as many available orbitals. But so, like, for example, like, I don't even know if the IB respects you to know this, but like Fe2 plus, when you react with Cl minus, you're usually going to have something like this.
Okay.
Like 4 Cls or 4 waters. And like Fe 3 plus will usually react with like 6 waters and form something like this. Now, you do want to kind of be able to figure out the oxidation number of the metal based on the ligand, right? Because the ligand, knowing the charge of the ligand will help you determine the oxidation number of the transition metal.
Yeah.
Okay.
Okay. Well, I thought that, like, I don't know, I was looking at the notes in the review book, and I thought it was saying that, like, it's always an octahedral, like it's always 5 ligands, no matter what the transition metal is.
No, that's not right.
Okay.
Well, I mean, it's not 5 wouldn't be octahedral anyways. 6 would be octahedral.
Well, five ligands?
Yeah, that wouldn't be octahedral anyways. 6 charge centers is octahedral.
Let me
So
find-
like this would be octahedral right here, because you have the waters in this 3-dimensional shape of octahedral.
Okay. Oh. Yeah.
Yeah.
Okay. I don't know why I said 5. It's yeah.
It's okay, rookie mistake.
God.
Okay, what's the next question?
I have one from Caroline.
Okay, what does line want?
So it says, can you explain convergence limit to calculate ionization energy?
Oh, okay. So convergence limit, essentially, remember, the energy levels converge here. And so, can I zoom in? I don't think I can zoom in. It's hard to see from YouTube. I can't zoom in anymore. Like, is it really that hard to see? Hold on, let me see what it's look like right here. Like, is it?
I mean, I can see fine. I mean,
Yeah,
I
it
don't
doesn't. I don't think I can zoom in anymore. Let me, cause like, yeah, my screen is set up. So
Caroline says she can see fine.
okay, just go full screen. Yeah, if you just go full screen, you're okay. All right. So the idea with that, all you need to know is like what they'll give you is like the convergence limit. Remember, so the ionization energy is the energy it takes to remove the electron, and so that all you're looking at is E equals h nu, and then C is equal to lambda nu. So like they'll give you an energy, then ask you for the wavelength of the photon, or they'll give you the wavelength of the photon, and then ask you for the energy of the photon. So that's mostly just kind of a calculation. If I'm interpreting that correctly.
Okay, she says she got it, and she takes physics, so she should know it anyways.
But so yeah, usually what they'll do is they'll give you the ionization energy line, and that's kilojoules per mole though. So you remember you need to convert that by converting to 1 mole to 6.02 times 10 to the 23rd, and that gets you, well, and then convert to kilojoules as well. So 1 kilojoule is 1,000 joules, and then that gets you the energy of convergence. And then you could use that to solve for the wavelength.
Wait, Trung?
Yeah.
So what would be the question there?
Like they would say, like the first ionization energy of like sodium is 1,312 kilojoules per mole. Determine the wavelength of the convergence limit of the photon that would be needed to remove the electron.
Okay.
So that's the energy at which everything converges at, because the ionization energy is the maximum energy before it escapes the atom, right? So that's the limit. That's what we call the convergence limit, because that's the limit of all the energy levels. Does that clarify?
Yeah.
Okay. Okay. Sarthak, can you go over the stuff we need to know about
What?
AR?
What is it?
I don't know. Um, let's see. I think that's like a mist type or something like that. Oh,
Maybe
Devin's.
argon?
I don't know. I think he means IR, but benzene.
Oh.
Well,
About
Did he mean
very similar
Aries?
to AR.
you mean arenes? I guess. Like I mean, okay. So with benzene, you're talking about the resonance structure of benzene. Okay, and so the fact you have the delocalized um, p orbitals, which cause the resonance here, as diagrammed by these this region here. And arenes are essentially any cyclical resonance structure. So benzene is one of them, and then like a bunch of other arenes that actually I don't know if I have a diagram of them that are included as well. I thought I had another one here. But so yeah, any essentially cyclical resonance structure is considered an arene, but benzene is one of them. For a higher level, you need to know the reaction of benzene for the the nitration of benzene. So for a higher level, you need to know that mechanism that we talked about kind of briefly. This came up in the afternoon session as well. Oh shoot! I wonder if wait, why does this hit? Okay. Hold on. Okay, maybe that works. Okay, so you need to know the nitration of benzene. So remember, this is with HNO3 and sulfuric acid. So the HNO3 with sulfuric acid forms this positive NO2 ion. Okay, and I have a feeling this is going to be on the test because it's one of the new things, and so they're going to try to do the mechanisms and stuff like that of this. And so this undergoes electrophilic substitution, and we'll talk about why that is in a second. But so the lone pair, the double bond of the benzene reaches out to nitrogen and binds to it. Okay. Oh, wait, you want to mute that, Kia? Or yeah, Kia, you probably want to mute that. Or is that?
What the hell are you doing here? Can I get my face out of here? Can I get?
You can disable your. You can disable your.
And get a headphone or something.
Yeah, you might want to get a headset or something like
Oh
that.
my god! Stop showing my face. I'm trying to turn this off.
Disable your webcam. Just go up to the top menu. Just turn camera
I'm
off.
on my phone.
Oh, that's hide from broadcast. There you go. Oh my gosh. Okay.
I need to
Alright.
see my screen. What the hell?
Yeah.
Oh.
Okay. Anyways.
Hide from broadcast.
Hey everybody!
Hey Abraham.
Diagram.
Okay. So
See
the
my
base.
screen.
Wait. Okay. Yeah. Mute the YouTube video. Here we go.
Hey everybody!
Hey Abraham. Okay. So the base. Wait. Okay. Yeah. Mute the YouTube. There. You go. No, not your.
Okay. So. You know what? Fuck it.
I thought I turned off your camera, but Abraham. Okay, Abraham left. Okay, anyways, so are y'all still with me so far?
Not really.
Okay, so the nitration of benzene. So what happens through a mechanism is that it forms this NO2 plus ion. Okay.
Wait,
And
what?
so-
The nitration of benzene?
Yeah, that's a mechanism.
Okay.
Okay, so this is nitration of benzene. Okay. So You can look back at what actually happens with the HNO3. It breaks off of water and forms this NO2 plus ion. But then the resonance structure, the double bond of the benzene, seeks out that because it's an electrophile, a nucleophile, and this is your electrophile. Okay, so then it binds to this, forming this kind of this cation, and then the sulfuric acid conjugate base will come in and take off this H, and then reform the resonance structure like that. I think I just had it as base here. But I'm not sure if the textbook just has it. Either way, but so. Okay, I'm gonna mute Keon for now.
Wait, so what is this used for?
This is just a mechanism because they wanted to implement more like practical application for benzene.
Mm-hmm.
So they included this mechanism now.
Oh.
And like the theory is that the stuff that's on the specimen paper isn't going to show up on the test, and so this is the other mechanism that you would need to know. I mean, because the specimen paper had the SN1 reaction, right? So, and this is new material, so they're going to want to make sure that you study this, and so that I'm thinking that it's going to be on the test.
Okay.
Okay, so then you can take that also, and you can reduce it using tin and hydrochloric acid, and then sodium hydroxide, and you can form the amine like this, aminobenzene. Yeah. I muted Keon, so I mean, if you want to type Keon, you can. Just because if you're on your phone, it's probably not the best idea to do this.
Wait.
Wait, did I unmute you?
No, I think I accidentally unmuted myself. Wait, hold on. Let me mute myself again.
Okay. Okay. All right. So yeah, that's the stuff you need to know about benzene. Sarthak, I think that was his question. So it can't undergo electrophilic addition because electrophilic addition would break the resonance, and that's bad. So benzene can't undergo electrophilic addition, but it undergoes electrophilic substitution.
Mr. Trong?
Yeah, shoot.
How do you determine like how polar a bond is?
Electronegativity.
Okay.
So you will look at the polarity of the bond, and then you'll look at like the overall molecule to figure out whether there's a so electronegativity is for bond polarity, and then like bond polarity vectors is molecular polarity. The best example is something like CO2, because CO2, the oxygen is more polar in both directions. But since that's the case, those cancel out. Okay. So therefore, there's no overall polarity of the molecule, and that's why this is considered nonpolar.
So when you're talking about bond polarity, and you determine that with electronegativity, is it just the difference in the...
Yes.
Okay.
Difference in electronegativity. So that's that spectrum we talked about from 0 to 0.4 being nonpolar covalent.
Okay.
And then 0.4 to 1.6 approximately is polar covalent. And then ionic is past that.
Mr. Trong?
Yeah.
I just wanted to see if you guys can hear me.
Yeah, I can hear you fine.
Okay, cool.
Okay, yeah. But so, Claire, like most likely on the multiple choice, if they ask you about it, it'll be like, which of the following has predominantly covalent bond? So you look for two nonmetals essentially, because you're not going to have the the electronegativity values in paper 1.
Okay.
Oh, Mr. Strong, question.
Yeah, shoot.
So I'm looking at the lattice enthalpy, and so the smaller the ion,
Yes.
the higher the lattice enthalpy. Why is that?
Well, because remember, lattice enthalpy is the attraction of the ions, essentially, because it's the amount of energy it takes to break apart the solid ions into gaseous state, right? And so think of it physics-wise is essentially Q1, Q2 over R squared, right?
Okay.
So the smaller the radius, the closer the ions can be attracted to each other. So
Okay.
the larger the charge, the smaller the radius.
Oh, okay, yeah, now I see. Because if they were bigger, like the protons, the nucleus would repel each other, like also, right?
Well, it's just the charge wouldn't be, the attraction wouldn't be as strong because they're further
Right.
away from each other.
Okay. Thank you.
No problem. Okay, Claire, you got something else?
Okay. So for the different processes that we need to know, we definitely need to know the Haber process.
Yeah.
Just what are the other processes that we need to know?
I mean,
Contact.
like industrial wise, it's like contact and Haber, but it looks like they've taken out the fact that you need to memorize the conditions,
Mm-hmm.
but you still need to be able to apply them. So they could tell you the conditions of the problem, you still need to explain them. Okay? So
Okay.
what I think of here is when I think Haber process, I think equilibrium, and then uses of ammonia. Okay? With contact process, well, I guess an enthalpy of reaction as well. But with contact process, it feels like that is more going toward environmental use applications. Because remember, the contact process is, well, actually, this, which then reacts with water to form sulfuric acid. So that's part of acid deposition there. And so I feel like that's the direction they would go with the contact process, and knowing the methods of cleaning it out and the methods of removing sulfur and stuff like that. Yeah, yeah.
That's how you would clean sulfur?
Well, no. So they probably tie the contact process. They might do some math and stuff like that, but then at the end they'd be like, the contact process can also happen naturally in combustion of coal. Explain one or describe 2 ways to reduce the amount of sulfur dioxide produced as emissions. So remember, there's a pre-combustion and post-combustion methods of removing sulfur. Remember, pre-combustion is that foam.
Oh yeah.
And so, let's see. I think I added those in here. I don't know if these are organized by dates. That's not what we're doing. Or did I just put them in oops? Did I just put them up here? Where's the? Oh yeah, the foam here. So there's the pre-combustion, and so you use water, which attracts the coal to the top, and then the oils and everything like that, the impurities sink to the bottom, and you're able to scrape the coal off without the sulfur at the top. But then also you can do post-combustion, which is the scrubber. Oops, that's the same picture. Remember the scrubbers, you use calcium oxide,
Okay.
and then you make the calcium sulfite, which then is solidified, and then you can clean that out. Yeah, so if I were betting, they're going to have a lot of environmental applications, because they really they took the entire environmental application and kind of dispersed it across. They're really trying to have real world applications here. So there's probably going to be some acid deposition thing on there, and then probably methods of like what are natural and man-made sources of the pollutants, and then like what are the reactions that occur to form the pollutants. So like remember like nitrogen-based nitrogen is can be from decaying vegetation or combustion of in the internal combustion engine, because it makes NO and NO2. Remember, sulfur can be from volcanic eruptions or the burning of coal, because there's sulfur built into coal. But so those, like, I mean, I guess if you really want to talk about processes, I guess you could also put in there addition polymerization. Because remember, what do you need for addition polymers?
You need a double bond.
Yeah, an alkene, right. And that is important because the manufacturing of those polymers are best used for what?
For like plastics and stuff.
Plastics, exactly. Okay. And so then, like, I mean, you could talk about, well, condensation polymers is a little more biochemistry. You could talk about hydrogenation. Don't forget that. Remember hydrogenation of fats?
Yeah.
So that way you can increase melting point and boiling point, decrease rancidity, increase shelf life and stuff like that. Okay. Other processes. You know, just combustion in general. You know, because you've got your complete combustion. That's producing CO2 plus H2O, unless they decide to put ozone in there again. And then you have your incomplete combustion, which is your CO plus H2O, and then your C plus H2O as well. Like they might ask about the health effects of incomplete. So CO, remember carbon monoxide is toxic to inhale because it replaces oxygen in the hemoglobin. And then carbon itself is just a carcinogen as well, like solid carbon. That's how it affects miners and things like that. You know, like they used to have the canary for mines and stuff like that.
Oh
Whenever
yeah.
the canary died, it was the concentration of carbon in the air was too high. And those particulates like lead to carcinogens in the lungs and stuff like that. Coal miner's lung. Okay. Fire away. I mean, if you got anything, Abraham, you got anything? Go ahead.
Is hydrogen bonding a van der Waals force?
Yes.
Okay.
Yeah, van der Waals encapsulates all the simple covalent molecule forces.
Okay. Oh,
yeah.
sorry. Is dipole-induced dipole the same as hydrogen bonding?
No. Dipole-induced dipole is when you have mixtures of things, and like one being dipole and one being kind of non-polar, and the dipole, the polar molecule induces a dipole into the other molecule. So like you have something that's polar, and then something that's non-polar, and then the attraction here causes this to become slightly polar, and so that a weak attraction is formed there. That's dipole-induced dipole.
Is that? I mean, that seems kind of similar though to. Oh well, I guess it's not because in hydrogen bonding there's already those.
Yeah, hydrogen bonding is a super strong dipole-dipole.
Okay.
So like there is a huge positive and huge negative attraction there, which then attracts.
Which is due to their electronegativity, right?
Yeah, the difference in electronegativity. So this attraction right here, that's your hydrogen bonding right there.
Okay.
Oh, Bernie Sanders just won Virginia.
Thank you. That will be included in this YouTube video for all time.
Mr. Tron, can you answer this question for me? Can you see it?
Oh yeah, hold on. I think I can. Okay, hold it still for a second. What should be changed to alter the rate of nucleophilic substitution of tertiary halogenoalkanes? Okay. The idea there is okay. What you got to remember is that with that's the leaving group. If you change the leaving group here, that will affect the rate because the nucleophile, which is the OH, remember, is not in the rate of the reaction because
Oh,
it's SN1.
you're right. Yeah. Tertiaries are SN1. Okay.
Right.
But the answer is the concentration of the tertiary halogenoalkene.
Yeah. Wait. Oh, it asked for rate. Wait, no. Hold on a second. It said the rate of the reaction.
Yeah, it said what should
Oh.
be changed to alter the rate of nucleophilic substitution of tertiary halogenoalkene.
Oh, okay. Sorry. Okay. So I was on the right track, but I think I misunderstood.
Yeah, no, I mean you're still
So-
right. Like the nucleophile wouldn't affect it, but
Yeah.
why is it that?
Because that's the only thing in the rate law. Because remember,
Yeah, you're right. Mhm.
the first step is breaking off that. But there was no leaving group in the answer choices, was there?
No, it
Okay.
was just concentration of nucleophile,
Yes.
size of the reaction.
Yeah, I was gonna say like the leaving group also changed it, but that's not one of the choices.
Yeah.
So
Okay.
okay.
What's
Thank
the
you.
answer?
The
It's-
answer is the concentration of the tertiary halogenoalkane.
Oh, okay. I think I see that. Yeah.
Yeah, because in SN1, the nucleophile, which is this, is not part of the rate of reaction. Don't worry, Sam. This is higher level. Sam's probably looking at this as like,
Oh, drop.
what?
Yeah, I was like,
No, so this is higher level. Okay.
alright,
I'm trying to,
All right, thanks, Mr. T.
cool.
yeah,
I
no
like
problem.
it.
Do you have any questions, Sam, or you just kind of here watching?
No, I thought it was cool.
Yeah.
No, I have to study math. I'm screwed for math tomorrow.
I can't help you with math.
Yeah, alright. I'll see.
All right, see ya.
Tom, I thought you could help with anything.
I can, but I don't want to. There's a difference, I guess. Because we got chemistry. We got chemistry here. Like, I'm trying to think. I just think there's definitely going to be some. Oh, there's Sarthak.
God, Sarthak, no.
We'll see what he says. I can kick him from the college if he doesn't stay on task.
Actually, wanna
Maybe
get
he doesn't even have a mic. Maybe he's just going to type in chat. Maybe that'll work too. Okay, let's see.
Oh, he muted himself.
Oh,
Sweet.
smart. I guess he just wanted to hear it without the lag and stuff like that. Because I think YouTube has like a 15-second lag or something like that.
Yeah, it's pretty good for right now.
Yeah. So I'm trying to think. You know, I guess everyone in here is higher level, and so I would see something like I imagine they're gonna have a thermochemistry question
Oh, okay, so what are we talking about there?
where like for HL at least, like where you have a reaction that's like something like this, right? And so gaseous, and gas, or something like that. And they'll do several parts. They'll say A, determine the delta H using bond enthalpy or something like that. Okay? And someone will, yeah. And then B, they'll be say calculate delta S of the reaction. And then C will be calculate delta G of the reaction.
Oh God.
State whether the reaction is spontaneous.
Okay, so for H using bond enthalpy, you just add up the H-to-H bond and I-to-I bond.
Right.
Mr. Strong.
Yeah.
So there's a question here. It's which statement about a first order reaction is correct?
Yeah.
And so it says reactant concentration decreases linearly with time.
No.
But okay, why isn't that true?
Because if the concentration decreased linearly, that means the concentration wouldn't affect the actual rate. Because remember, at first order, as you decrease concentration, decrease rate, so the slope should be changing. If it's a linear decrease, then it's zero order, because the rate doesn't change at all.
I thought the concentration was like our x.
No, concentration is y, time is x. You're thinking of rate times versus concentration.
Oh yeah, isn't that the same thing?
No. That's where, like, concentration versus time, if you get something like this, that's zero order. Because you notice how the slope here is rate. The rate doesn't
Right.
change. So that's zero order. First order
Oh, okay.
would be this. Because you see how the slope is changing?
Yeah.
So it would not decrease linearly.
Okay, so it'd be an exponential time. Okay.
Yeah. Okay. State whether the reaction is spontaneous. E.
Thank you.
No problem. Give the equilibrium constant expression. Okay. Or state the equilibrium constant expression, I guess, if we're going with. Okay. Then F, calculate the concentration of HI at equilibrium if K is equal to 100 and H2 is equal to 1 molar and I2 is equal to 1 molar. Okay, I just made those numbers up. They probably don't make that much sense. But so here you have to think of an ice chart, right? So you have 1, 1, 0, minus x, 2x, 1 minus x, 1 minus x, 2x. But this, if you notice, what do you notice about this equation?
Oh, just the squares cancel out.
Yeah, well, not cancel out, but it's a perfect square, so you need to square root both sides. And then it becomes a simple algebra problem. So, yeah, you just square root both sides, then it becomes 2x over 1 minus x equals 10. And then you can solve from there. So it's either going to be 5% rule or it's going to be perfect square.
What would x give you specifically? Like, what is x here?
The change. So it would tell you what the if you subtract that from 1, that give you the concentration of H2 and I2 at equilibrium. If you multiply x by 2, you'll have the concentration of HI at equilibrium.
Okay.
Yeah.
So are we gonna go through all these A, B, C, D, E, F?
Oh, I don't have my data packet on me. I just kind of made up.
Okay. Okay. I think I understand everything except for B. How would you do delta S if you don't have delta G and T?
No, you would use S from the table. Like
Oh, so it just says state?
No. Like there are actually S values on the table with delta HF and delta GF. Like on the data packet.
Okay, so you'd use S from the table and you just put that down as your answer?
Well, you do products minus reactants.
Oh.
So like you multiply by the coefficient and you do products minus reactants like you would for enthalpy of formation. I guess you say calculate delta G of reaction at 298 Kelvin. Kind of important.
Yeah.
What counts for the rate in SN2 reactions? The nucleophile and the halogen alkane. Well, because you have to have the nucleophile attack the halogen alkane before it starts the reaction. So the reaction is dependent on the OH attacking the carbon. So both of these concentrations matter. So therefore, that's why the rate law is equal to K times CH3CH2Cl and OH minus. But in the SN1, you're waiting for the halogen to break off, then the OH attacks. Yes, you're right. SN1 is just a carbocation.
Oh, and just to make sure, this what did he say? SN2 reaction.
SN2 is concerted system, Sarthak. Wait, sorry. What'd you say?
For this SN2 reaction that you wrote on the screen.
Yeah.
Would that be you'd use a polar aprotic solvent?
Yeah, aprotic is the main part of it. Because if you have a protic, it would hydrogen bond.
Yeah, hydrogen bond to the OH.
Yeah. So this is your concerted system. Make sure when you write it, you draw it like this with the charge around it, because there is a negative charge to it. Because in this instant, both the OH and Cl are kind of bonded to it, but again, it's a transition state / concerted system. And then it breaks off, and then you produce the two products. And don't forget, two products. You form the alcohol and the OH, the Cl minus. You need to write that. SN1 reaction. So the SN1 reaction so the Cl breaks off first, forming the carbocation, because the nucleophile can't attack that because these CH3 groups are really large. So the OH can't attack that. And so then the OH minus will now attack this. So then you end up getting the alcohol and Cl minus. So the first step here, just think about the first step being the slow step, right? Think about what's happening in the slow step, and then you'll be able to find out the rate easily. Okay.
Mr. Trong.
Yeah.
So I heard you talking about the slow step.
Yeah.
So the rate, equation is determined by the slow step,
Yes.
or it's the addition of the slow step and the fast step, and then you find what the like.
No, that's only if the slow step is after a fast step.
Oh, is after. Okay.
Oh,
Okay.
sorry, I need to finish that. Hey, Sammy, how's it going? I don't know if he has a mic. It's just in here. But so, yeah, what we're talking about there, this is kind of devolved into a higher level session. But so, the slow step. So what you're thinking about here is, Abraham, is that, like, let's say you have a reaction like this. Okay, the overall reaction is 2A plus C yields D, which makes sense. This is higher level too, Sammy, don't worry about this. But so there are two options you could have. You could have this as a slow step, and that's a slow step, then the rate of the reaction is equal to K times A squared, because there's 2A, right?
Mm-hmm.
But if this is the slow step, you can't have B, because B is a what?
Intermediate.
Intermediate. And you shouldn't have an intermediate in a
Rate law.
rate law. So what does that be essentially equivalent to?
Okay. No, nothing.
No, what is it in the first step?
Squared.
What's it essentially equal to?
Oh, 2A.
Yeah, so then rate is equal to A squared times B.
Oh, B.
Yeah.
You mean C.
Oh, C, sorry, yes. Sorry, I was thinking about my old example. So C, yes. So you see how the rate laws change based on which one's the fast and slow step?
Yeah.
Yeah. You never use the coefficients of the overall reaction.
Oh.
You only use the coefficients of the slow step.
Oh,
Unless
wait.
there's
Of the overall reaction, only
Yeah.
well that only is if the slow step comes first, right?
correct.
Okay. Cool. Thank
See, no problem. Let's go over structures again. I feel like there's going to be quite a bit of stuff on structures, and this will kind of help Sammy as well when you're thinking about this. And so you want to think about electronic geometry, and then we'll do molecular geometries as well. So electronic geometries, you have linear, trigonal planar. Oh, Sammy left. Tetrahedral. Trigonal bipyramidal. And then, oh, that's a really bad one. Octahedral. Like, I really think that, like, there's, like, if you just remember these 5 shapes, you can figure out every single molecular geometry possible. I think it's really useful that way because, like, you just start covering stuff up, I mean, I'm just going to keep copying these. Copy, paste, paste, copy, paste, 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 copy, paste, 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 paste. Okay? So your goal is to always make the shape so that the electron pair is as far away from everything as possible. Okay? So for trigonal planar, actually, you know what? Let me change all these colors to pink. Because now remember, electronic geometries also, molecular geometries are included in there as well. So this is also a molecular geometry if you have no lone pairs on center. But so the goal is, again, to erase one line or cover up one line so that it's an electron pair.
Oh yeah, can we practice covering up like which lines? Because
Yeah.
I messed up that.
Okay,
math before.
so yeah, no problem. So trigonal planar doesn't really matter, right? Because everything's 120.
Right.
So we just have this. So what's left there, Keon?
Yeah, bent.
Bent. But what's the angle?
100. Oh whoa! What happened on my screen? 173.
It's less than 120, Keon.
Oh, so like 109.
Not that far. 117. What's up, bro?
Okay, 117.
Remember, you take away 3 degrees for every lone pair, and you should be safe.
All right, cool.
Okay? So 120 for trigonal planar, 117 for bent. Here, it doesn't matter either, so I'm just going to take that one away. Okay? So what's left here?
You got 3 of them.
Think in 3 dimensions, though.
Trigonal pyramidal.
Trigonal pyramidal. Okay? Now, tetrahedral is 110. So what do you think trigonal pyramidal will be?
107.
Yep. And then, now if you take this one away,
It
then
becomes
you can take any
bent
other one
again.
away. Yeah, bent.
So it's like 104.5. You said.
Yeah, 104.5 is sufficient. Yeah. Okay. So now the tricky ones are higher level ones, right? Because now you get like a lot more complicated. But the idea with these structures is, again, the lone pair, that the bond that's as far away from the other ones as possible. The ones on the top here are 90 from 3 and 180 from 1. That's not good.
Uh huh.
This is actually the best one right there. Because now that lone pair is 120 from 2 and 90 from 2 others.
So seesaw.
Seesaw, exactly. Oh, this is 90 and 120. Okay. So now the second one, you want to take away 2 pairs. Well, what positions would the lone pairs be at the greatest angle from each other?
Wait, for seesaw, would the angle change? Would it be 117 again?
Yeah, and like 177. But they're not going to ask you exactly for those numbers. They'll just ask you that it's less than 180 and like less than 120. So they won't ask you for exact numbers.
Okay, so the next one.
Okay, so what 2 points would lone pairs be as far away from each other as possible, but also as far away from other atoms as well?
I guess the next one on the 120 sequence.
Yeah, exactly. So guess what's left when you have here?
T-shape.
Yep, exactly. And now you take away the 2 120s, and you take that one away?
Yeah, linear.
Linear. I guess you don't need the last one. I made too many of them. My bad. Okay. What do you recommend me memorize? Oh my gosh. Like
so many things.
yeah, in shapes or like in all of IB chemistries. Sorry.
All of IB chemistry.
I swear if he says all of IB chemistry, I'm gonna kick him from the call.
Well, now what is he gonna say?
Like, I mean,
Boy.
yeah, he's not gonna say it now. He doesn't have the guts. But okay, so
Oh, my stylus.
in general, like stuff like, well, yeah, you have to know all your polyatomics. You have to know the shapes. You have to know like the electrolytic and voltaic cell. You have to know the Chatelier's principle. You have to know hybridization. You have to know organic naming. I mean,
He's saying all of IB chemistry.
a little bit, yeah. Okay, Keon, let's do this other one while he's trying to kind of process that. Okay. So, these shapes down here, octahedral. Does it matter where you take away one? Because they're all 90.
Yeah, they're all 90,
So we're going to just do that one, the top one. It's easier to see that way. Actually, you know what? No. Let's do this, okay? Remember how we said that we took from the side for the
keep on doing that?
Yeah, let's just keep doing that. Because it's hard to see it, but you can see there's a square.
Right.
That's here.
Square planar.
But you still have one other point.
So square. Oh, no, square pyramidal. What?
Yeah, square pyramidal. Exactly. Now, let's take away that, and now take away from the other side, because they're as far away from each other as possible, right?
So planar.
That's square planar. Make sure you say square planar, though.
Square planar, okay.
Okay. So you've taken away 3 of those now, and then you take one more away. What's that?
T.
T. And then you take away 4.
You linear.
Yeah, exactly. Those are your shapes.
Nice.
Yeah, so if you just think of the higher level ones, just cover on the around the equator. That's really easy.
Alright.
If you cover around the equator, you'll see the rest of it. I have a feeling like they'll find a way to kind of incorporate resonance in here. So like you'll have like ozone in here for standard level, and then they'll ask you for the shape. So the shape here for the electronic geometry would be trigonal planar. But the molecular geometry would be what?
Whoa. The electronic geometry we trigonal on the middle.
On the middle oxygen, yeah. Sorry, you should do with respect to the middle oxygen.
I guess.
Because it has 3 charge centers.
So
Then
Yeah,
Bent.
it's bent. Okay. So that would be something that's shows up in the on the shapes and stuff like that. And then like they could take that and like break that into like remember how on we talked about like the energy required to break the bond?
So basically delta H.
Well, remember though we converted it to the wavelength of a photon. So you take the bond enthalpy
Divided
Yeah.
by 6.02 centimeters to the third.
and then multiplied by 1,000 to get the joules. And so that energy, and then you set it to find frequency. Oh, I can't write that. Frequency, and then C is equal to wavelength times frequency. So
Then you can find energy using that.
yeah, so they would do that for a higher level. Standard level, what they probably do is give you the frequency of the photon, and then ask you to solve for wavelength or something like that, because you have to know this for SL, you have to know this for HL. So that's how they would probably do that. And then also, they could make you do like the mechanism between chlorofluorocarbons and ozone to show the breakdown of ozone as well.
Yeah, can we go over that, because that is
Yeah,
something
sure.
that I definitely like
Okay.
don't know.
So the idea is first, you have to have a chlorine, because the chlorine to carbon bond is what breaks. They'll write it like this just because that's energy. So it breaks up into the Cl free radical. Okay, so that's your initiation step. Your propagation steps, that Cl free radical seeks out ozone. And it makes ClO free radical and then O2.
Oh, so it's basically a free radical
Yeah.
mechanism.
So then that reacts with O3 to make Cl free radical plus 2O2. So you see how much ozone it's breaking down. And then the mark scheme also has this as well. ClO dot yields Cl dot plus O2. Because remember, ozone essentially is in equilibrium with O2 and O free radical. So there's O free radical present, which can also react with the ClO as well, and that's dangerous because it reforms Cl dot here. Because Cl free radical can break down quite a bit of ozone that way. Okay. Let's see. I'm trying to think of more kind of electron configurations. Trying to think.
Mr. Strong, I'm gonna have to leave for like 30 minutes to eat dinner.
Yeah, no problem. Go eat.
All right.
All right, I'll see you.
Yep.
Okay. Let's see. Elena, do you have some questions? Because this is mostly been higher level, but if there's something standard level that you'd like to talk about, just put it in chat or something like that.
Yeah, thanks. I missed the shape thing, so I'm just like rewinding on the YouTube thing.
Oh, okay. But you only need to know the top part of it.
Yeah, and I've really been focusing on that, so I think I'm good, but it's just like, I could always go the other way.
Yeah. Let's go over enthalpy, because that seems to be, well, actually, no one's here right now, but I have a feeling enthalpy will be a huge thing. And so what you want to think about here is the idea of, you've got, I guess, 3 different enthalpies you can solve for. Enthalpy of formation, enthalpy of combustion, and bond enthalpy. Okay? And no matter what kind of reaction you have, like, this is how I remember it, okay? I just write out an example of one of the the substances as that type of reaction, and then I see where the delta where they lie on the reaction. So if I'm doing enthalpy of formations, okay, I write, okay, what's an enthalpy of formation of C2H4 look like? Well, I make C2H4 from carbon, solid, and H2, gas.
Yeah.
That's a delta HF of that. Well, if you notice, the delta, this is on the opposite side of this.
So you gotta reverse it, thing.
That means you've got to reverse all the products. So that reactants. So what that tells you is that all the reactants will be negative, the products will be positive, because the products will be on the correct side.
Because it says products minus reactants, yeah.
Yes, and don't forget to multiply by the coefficients as well.
Yeah.
It's kind of implied, but I'm saying there. Enthalpy of combustion is the amount of gas produced. I mean, the amount of energy produced when 1 mole of the substance combusts with oxygen. And so here, 2, 2, 3. So notice the thing I have is on the same side.
Mm-hmm.
So then that means the reactants are the same. The products are opposite.
Yeah.
Bond enthalpy, well, if you look at H2, you break it up into 2H. Well, H2 is on that side. So all the reactants are positive and all the products are negative.
This chart is like a beautiful thing, Mr. Trong.
Well, I didn't, to be honest with you, I didn't come up with it until this year. This is something new that I've done. I've always kind of just said memorize it, but now with as much stuff as you have to know, I just think this is this helps you apply these definitions and help you remember which one's which.
Oh my god. Oh my god. Okay. Thanks, Mr. Chung. This is actually like super good for me.
All right, no problem. Because you're limited to what math you have to do for standard level. So I have a feeling that one of these will be that will be on there, some stoichiometry, maybe a little bit of equilibrium, but that's that's the gist of y'all's math for SL.
I know, it's wonderful. Good. I'm very happy with it.
Yeah.
I've been watching a lot of Richard Thornley.
Yeah, that's good.
He's like my favorite guy right now.
Yeah. He has everything broken down into really small snippets here and there.
Yeah, he's wonderful. Yeah.
Okay. Any other questions?
I'm just kind of doing practice papers.
Yeah.
I'm not really like studying to have questions. I'm just going like, oh, that's what I did wrong. That's what I did right.
Okay. I got to these questions in the book that talk about alloys.
Yes.
In my head, I don't know anything about alloys. Like, can't remember ever.
Yeah. See.
Know about alloys?
I didn't see much about alloys, but let me just double check here because alloys would be in here.
Oh, this is so cool.
And so the things that you really need to know, all you really need to know, it says examples of various alloys should be covered. Okay, that's kind of strange. I need to make sure I go over that tomorrow. But so you've got kind of two major types of alloys here. Okay. Okay. So you've got substitution alloys. Okay, where you have a metal substituting for another metal in the metallic bonding. So, like in bronze, that's copper and copper and tin. No, it's tin brass.
No, brass is zinc. Yeah, bronze is copper and tin.
Copper and tin. Okay, so what happens here is you have copper, and then there's some tin molecules in there now. So that's a substitution alloy. Okay. Interstitial alloys are ones where a small, generally non-metal, fills in the space between metal atoms. So, like, for the best example here is steel. So, like, this is where the carbon atoms fill in the spaces between them. And so, those are the two types of alloys that you need to know. That's weird. It wasn't on the syllabus tracker, but that is something that's technically on the guidance here and there.
And do we need to memorize what makes what alloy? Like the metals you said that make a substitution alloy?
No, I don't think so. I think because they're trying to minimize what you have to memorize, right? So, I don't think you need a specific one, but if you just have a couple in mind, you should be okay. And so, examples of various alloys should be covered. So, yeah, like steel, bronze, brass, and stuff like that. But I don't think they're going to ask you like what is reacted with like copper to make bronze or something like that.
Right.
But then again, like the alloys are useful because like when you add those metals, you add strength, luster, and things like that to it. And so it's useful because like metallic bonding is non-directional. It's not like a crystal lattice. And so like it gives it malleability, it gives it conductivity because like when you hammer it, the non-directional bonding just spreads out and makes it thinner and thinner and thinner. So it doesn't like break anything. It's very malleable.
This might sound really weird, but can we talk about buffer solutions?
Yeah, sure. Sorry, Elena, this doesn't affect you.
Oh, I mean.
I'm so happy with that. Don't worry about that.
No, I think she's just kind of here and there, so don't worry.
Yeah, I'm listening, but like I'm studying, but I'm listening.
Yeah. Okay. So, Hamid, what do you want to know about buffer solutions?
I haven't gone.
Wait, you muted.
Oh shoot, sorry.
Yeah, it's okay.
I haven't gone to chapter 8 yet, but
Okay.
just flicking through it, I saw like the calculation of the when you like on the graph. I know the equivalence point is the part where it's almost vertical.
Yeah.
But then that's not the buffer zone. The buffer.
No. Yeah, this is something we talked about, I think, after school, and this is what I want you to kind of think about. So let's do a strong base with a weak acid. Okay, a titration. Okay, so you'll start down here. We'll go up, and then flatten out. Right? And the equivalence point should be a little bit higher than 7. Because strong base and weak acid makes a basic salt.
Yeah.
Okay. Now, there are 3 major points that you need to know on here. Okay, and I want you to talk about like what's present in the solution. At this point right here, A, what you have in the solution is almost 100% of HA and a little bit of A minus and a little bit of H plus, right? Because the weak acid doesn't associate very much.
Yeah.
Okay. At this point right here, you've now gone to 50% of HA and 50% of A minus. And at this point, all you have left is A minus. You see what I'm saying there?
Yeah.
Okay. So key things here. This region right here is the buffer region because you have HA and A minus. I mean, I guess I probably wouldn't go extreme here because once the curve starts going up, it's like very sensitive. So kind of that region is the buffer region because you have HA and the A minus. So like if you have HA it will react with any OH to absorb that and form H2O and A minus. If you add any acid, it'll react with A minus and form HA.
And the way you solve for that is you just set the two concentrations equal to each other, or
What do you mean?
like if they tell you to find do they ask you to find the equivalence point, or like is there somehow mathematically some way to solve for the equivalence point?
No, you just read it from the titration.
Okay, good.
Yeah. I mean, I guess you could if you did like A minus plus H2O yields HA plus OH minus and took the molarity of A minus and then used KB. I guess you could technically solve for it that way.
Let's see.
Okay, now Hamid, this point right here is approximately halfway to the equivalence point.
Mm-hmm.
And if you have HA is equal to A minus, then KA is equal to A minus times H plus over HA. But notice if HA and A minus are the same, KA is equal to H plus, or pKa is equal to pH.
I see.
Wait, and Elena, I don't understand your question necessarily.
Oh, we did that, like we drew it with arrows. It started with like alkene, and then it went through, and we kept going, and how everything connects that we learned.
That
thing.
would be in the.
I've had it open for days, but then I closed it, and then I was like, oh, I need it.
That's organic chemistry topic 10.
Okay, that's it. Okay, thank you.
You can choose any of them, which I think you're section 2, and it should be at the very
Okay.
bottom here.
Awesome. Thank you, Mr. Tron.
Yeah, no problem. Okay.
Yes, that's it. Beautiful.
Yeah.
Thank you.
So Hamid, does that make sense?
Yeah, it makes more sense now. And now so the Ka tells you, is it how much of the acid is dissociated at that?
Yes. How much the acid would dissociate in just a solution of water.
Okay.
Now here, this tells you the H plus concentration initially, and also that equals the A minus concentration as well.
Yeah.
So I guess
those are
if you
some-
knew the pH here, you could solve for the Ka because you know the concentration of H plus and A minus because they're the same over HA. You could solve for the Ka that way too, but that's a lot less accurate.
And how would you get the concentration of HA at that point?
Well, you'd have to do like the original molarity and subtract the H plus concentration from it. But I think that's pretty inaccurate.
Okay.
Keon, I think you've heard all this stuff before, so I don't think you missed
Oh.
much.
Oh yeah.
Well, actually, the only thing that something that we're probably gonna have to review in class tomorrow is alloys, because like the IB is really vague on it, but you need to know the two types of alloys. So substitution alloys, where a metal substitutes for another metal. You're probably familiar with that in bronze and brass. Then interstitial ones, where a small nonmetal fills in the space between the metal atoms, which makes it stronger, rigid, makes it harder, but less flexible. So as soon as you do meet the force that breaks it, it will snap.
Oh.
Yeah. Whereas substitution alloys more kind of change the physical properties of it, and it's less so of the flexibility and the hardness of it.
And what's the stuff before that?
Oh, that was just my review about how to do all the different types of the enthalpies of reaction. You know, I think we talked about this in your lesson, maybe not, but like how like I just remember the definition of enthalpy formation, enthalpy combustion, enthalpy bond enthalpy, and then I just write one reaction for one of the species, and whichever side the species is on, then I can tell whether it's reactants minus products or products minus reactants.
Oh, yeah. You talked about that.
Yeah.
All right, chill. I'm gonna review for Math West. I'm gonna get like a 4. So.
No, God, you'll be fine. Good luck, man.
All right, I'll be back.
I don't know how much longer we'll be on.
Okay.
Because it's already like 9:30, and I don't want to keep y'all up too late because you got math tomorrow morning.
I mean, it's oh shoot, it's past your bedtime, right? I mean,
No. I stay up later than this week.
yeah, I know. I think I'm gonna go have dinner and then study a bit more for Kim.
Yeah, no problem.
Get to the end of chapter 8.
Okay. Good luck.
Wait,
Thank you.
Mr. Chung.
Yeah, Elena.
Just review with me really quickly.
Yeah, no problem.
So primary alcohol is just just a primary. Oh, I guess alcohol. Yeah, it's when it connected to like one other carbon. Secondary is connected to 2 others, and tertiary is connected to 3 other ones.
Yes.
Like that's a primary because it's connected to only one. No, that's a
No,
secondary.
sorry. I started writing it.
Okay.
Yes, correct.
Okay, great. Then that's it. I don't know. What do you think I should review the most and strong? Like, what do you think trips people up?
Gosh. I think priority at this point is topic 10, then 4, then 6, and then 7.
10, 4, 6, 7. Okay.
Yeah. Because those also have probably the most. Actually, 6 doesn't have a lot of new stuff, but wait, no, not 6. I'm sorry, 5. Did I say? Because 5 is thermo.
Yeah.
Because I say 5 and 7 because that's where a lot of your math is, right? Because calculating equilibrium constant from using ice chart, doing bond enthalpy, enthalpy of formation, enthalpy of reaction, calorimetry, and stuff like that. That's important. 4 is shapes and bonding and types of bonding and IMFs.
Energetics.
10, 5 is energetics. 10 is organic, and I know there's going to be a bit of organic on there. And so, naming, homologous series, substitution reactions.
Is 7 equilibrium or acids and bases?
Equilibrium. I guess 7, 8 is kind of together for you because for standard level, you don't do much with 8 other than like the properties, the reactions, and then acid composition.
It's great.
So,
It's beautiful.
yeah, and so 7, 8 would be kind of the combo here.
Okay. 9:30, Mr. Trong.
Yes. Is there anything else I can do for you, Elena?
At this point, it's too late to switch into an bi-sci, so no.
Sorry to hear that.
Okay. Okay. Bye, Mr. Trong. Thank you.
Bye.